Hey everybody, we are in chapter 7 and we're looking at polynomial functions, and of course this is algebra 2. Let's get right down to our vocabulary. So we're going to be talking about polynomials, and here are a couple examples of polynomials. So these three are pretty decent examples of what a polynomial is. It doesn't really define it for us, but what it does let us know is what it looks like when we see it. The word poly, obviously meaning many, nomial, number, many different numbers that are being added and subtracted together, but that's not really enough. The fact of the matter is, when we're dealing with a polynomial expression, we're going to make sure that the variable terms that are involved have whole number exponents that are neither fractions nor negative, right? So if I said whole number, obviously I mean not fractions, but the negative part is also important. So notice that we have that. The variables all have positive whole number exponents. That's cool. Things are being added and subtracted. No variables are being divided into the expression, and we can definitely have constant terms, regular numbers that are hanging out by themselves. So these are all examples of polynomials. Polynomial expressions rather, and the ones that have only one variable are, got it, polynomial expressions in one variable. And so in this case, we will be looking at this as an example and this one over here as an example. And the next term that we're going to talk about, I'm going to erase this one, though it's a polynomial, it just doesn't fit that definition. All right, so the next thing we're going to talk about is the degree of the polynomial. Let me get a nice highlighter here. When I'm talking about the degree of the polynomial, what I want to do is to determine what term has the greatest number of variables in it. So as I look at this term, this is 3x's, this is 2x's, the next one has 1x, this has x to the 0 power or no x's. So this term would tell me the degree, and in this case, the degree would be 3. Does that make sense? It's a third degree polynomial. And over here, if I looked at this next one, I go again to the highest variables, or the largest number of variables that are collected together in a term, and I see that that would be 2t's there. So the degree of this particular polynomial is 2. Now when we get to the lead coefficient, I'm going to highlight here, let me use a thicker pen. When we get to the lead coefficient, what we're talking about is the coefficient that is associated with the term that gives the polynomial its degree. Kind of the biggest and baddest variable coefficient is the one you want. So for us, the lead coefficient for this first equation here, or this first part of polynomial expression, is not an equation, would be 1/2. And the lead coefficient here would be 4. And it gets its name in the fact that when we write these in descending order of power, the lead coefficient would literally be in the lead. So if I were to write this from greatest to least, I would have 4t squared minus, well, let's join like terms together, 3t minus 10t plus 9. And this is how we would write this expression, and you can see that this coefficient leads. Similarly, I could rewrite this term, and well, no, I don't have to. It's leading right there, all right? Making sense? If I have a polynomial function, hopefully this makes sense. Polynomial function is just an equation where we have a polynomial in it. For example, this equation right here would be considered a polynomial function. It has a polynomial. It's written in f of x form, which we generally reserve for function notation. And so hopefully that makes sense. This next guy is not really a quick fix, short way to answer it. But when you think about the graphs of polynomial functions, and so those graphs can look like this, all right? And I know these are strange names. I'm going to just give you a quick breakdown of what's going on here. So a 0-degree polynomial would be like, or a polynomial function would be a constant function where f of x or y is equal to some number like 7. And so we know that if we were graphing y equals 7, it would be a horizontal line through, let's say, the number 7. And this looks very much like a y equals mx plus b situation, or an f of x is equal to something like, I don't know, I'm just making stuff up here, but 2x plus 7. Let's say this is 7 and the slope of this bad boy is 2x, or is 2, then we have this equation. This is obviously a quadratic function. F of x is equal to some ax squared plus bx plus c. This is something that we haven't dealt with, but a cubic function. So you get the idea that we are just moving up in power, right? You see, this is x to the 0 power, x to the first power, x to the second power. If the degree here is 3, this is going to be x to the third power. So I'm just writing a generic form. I can have y equals ax cubed plus some bx squared plus some cx plus some d. And I can continue on where this guy would have ax to the 4th power plus bx to the 3rd. You guys see where I'm going. And this quintic would have y, or f of x, is equal to ax to the 5th power. And I keep going. My point in showing you this is to give you the idea of what end behavior is. So when we consider end behavior of any of these functions, what we're thinking about is what is happening to the function itself as x goes out to either positive infinity or negative infinity. So let's look at this example. As x is going out to infinity, meaning as x gets larger and larger values, and I plug it into this function, excuse me, what is my y value? What is my f of x value going to be? Since this is a constant function, it's going to remain constant. So f of x in this situation, and if I had this equation, it was equal to 7, it would just be 7. F of x would continue to be 7. Similarly, if I were to consider what happens as x, what's the end behavior as x goes out in the negative direction, this thing ain't changing. F of x is still just going to be 7. All right, so that's what the end behavior or the expected future behavior would be for our equation. Over here, we'd say the same thing. If I started, well, not the same thing, we consider the same thing. I'm going to consider as x approaches infinity, what's happening to my function. So the larger and larger values I get for x, what's happening with the corresponding y or f of x values. As x goes out to positive infinity, f of x is going out to positive infinity as well. Can you take a guess what's happening as x goes out to negative infinity? And that means going back this way. What are the values? What's happening to my values of y? The larger the x values go, I get this x value out here, I'm down here with y. This x value down here with y. As I go out to negative infinity, I'm hoping you're guessing that I'm going to get negative, as x goes out to negative infinity, y in this case is going out to negative infinity. Now that's not always the case, y'all, right? Think about it. What if this function were to be, to have a negative slope, right? So I'm gonna just quickly try to take this away real quick and think a little bit about what it would be like. So if this graph wasn't this positive slope linear equation, I had some negative slope linear equation like so, right? My end behavior would be different. As x goes out to positive infinity, as x is going this way, f of x would be going to negative infinity because it's going down. Are you guys with me? I hope so. And similarly, as x goes to negative infinity, f of x on this side, because I'm going to negative infinity with x, f of x is going to positive infinity, right? It's just going up forever and ever. Whether I have a happy parabola, as you guys are used to me saying, or a sad parabola, right? I'm going to have different in behavior. Notice this. I'm going to have either a positive, as like if we look at the blue function, let's go ahead. As x goes out to positive infinity, f of x is going out to positive infinity. But as x goes out to negative infinity, f of x is still going out to positive infinity. It's going up, y'all, right? Is going out to positive infinity. I don't know if you're seeing all this is looking pretty sloppy over here, but you get where I'm going. However, if I had this sad parabola, as x goes out to positive infinity, f of x is going down to negative infinity. So when we talk about end behavior, we're talking about what's happening overall. Like when x gets super, 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 super big, or super, 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 super small and negative, okay? I know that was a lot of chatter. Thank you for staying with me for that. Let's get back to our work. All right, after all that talky, let me see if we can get into a couple of examples. Let's find the degree and leading coefficients. We're going to state the degree and leading coefficient of each polynomial in one variable. If it is not a polynomial in one variable, explain why. All right, so here we do have a polynomial in one variable. I can see all the x powers are positive and whole numbers, and nothing's being divided in the denominator, we're good to go. So what we need to do is just do the degree and the lead coefficient, which is easy for us because we paid attention to the prattle at the beginning. The degree is 4 and the lead coefficient is 7. All right, and I'm just going to put the LC. LC is equal to 7, and I think that's pretty straightforward. Let's look at this next one over here. We only have to do it if we have a polynomial in one variable, and we do not have a polynomial in one variable because this polynomial has variables of x and y, so we don't have to do anything with that. Let's look at number 7. Part C, which begins with number 7. 7x to the 6th power minus blah, blah, blah. All right, children, just stay with me. All right, so is this a polynomial? It looks like it, but it's not, because this x down here, and right now you might be saying, oh, but that x is to the first power. Technically it's not. X is really to the negative first when we've got 1 over x. You remember that back in the day? All right, hopefully you do. And so this is not a polynomial. Remember, a polynomial, all of the variables need to be being raised to a positive whole number, and this isn't. All right, so we don't have to do anything with that. And finally, here's one we do have to deal with. This is a polynomial in one variable, just x, and we need to figure out what the lead coefficient is and what the degree is. I'm going to rewrite this kind of in descending order as we talked about before. I think it makes things easier to see. And so once I do that, it's pretty obvious that the degree is 5 and that the lead coefficient is -1. Cool. I hope that felt easy for you. I thought you're like, yeah, this is boring. All right. All right, one of the things that's important for us to be able to do is to evaluate functions. And so this is a skill that you've probably been working on since 9th grade or whatever grade you had Algebra 1 in. So check this out. If we have f of r, so here's a function where the function f is dependent on r. R is the independent variable. We have 3r squared minus 3r plus 1. And we're asked to figure out what the value of, this refers to hexagons when you have what is it called? When you have a beehive, but we're not really worried about the context at this point. I really just want you to be able to evaluate f of 1, f of 2, and f of 3. And what I generally do whenever I get into a jam, when I'm dealing with these types of problems, I know that whatever value's in here needs to be placed throughout the polynomial expression or the polynomial function I'm evaluating. So what I do is I just put open parentheses around the variable that I should be replacing, or in place of the variable. So I just drop the 1 in, right? If I had those same open parentheses situations for each of these other expressions, I would just drop whatever value is here. And this is pretty like, yeah, this is easy. But the reason why I like to do it this way is because sometimes you'll get goofy things like, if f of r is this, what is f of r plus 7 minus 3? Or 3r or something squared. And you look at this and you're like, what am I doing? It's the same exact thing. If you had something goofy like this, if you had to evaluate this, given this, literally write down what you're supposed to write down in terms of write the expression with blanks for the variable, and then just drop in the thing you're supposed to drop in. And so in this case, we got to drop in all of this business. And you literally just substitute it in there, and then you simplify it as best you can. And so if we were to do something like that here, well, this is much easier. We're just going to calculate the value, and the values here are written here in red. Here are the values that we would get once we calculated that. So we only have a couple more examples to talk about before we end this particular section 7.1, and I think I'm going to take it up in another video just so I have a little bit more freedom of time. So check me out in part 2. I'll talk to you in a minute. Bye-bye.